So hi, my name is Nicolas, and I will present you some joint work with Francis Bach. So our goal is to minimize the sum of two functions. The first of one is the expectation of non-strongly convex quadratic function, and the second one is a simple convex function, in the sense that we will define after. So if we consider that the function f is deterministic, so f if convex, else smooth, and J is convex, if we use the subgradient method, we will not leverage the structure of the function, and we will not use the fact that f is smooth. So instead, we can use proximal gradient descent, where the smoothness of f will be used, where the next iterate will be the minimization of the second order quadratic upper bound of the smooth function f plus the function g. And so this algorithm is only practical if we know how to solve this problem in closed form. So for example, if G is equal to the indicator of a convex set, we obtain the projected gradient descent. Or if G is a threshold gradient descent, we will is a one norm, we will obtain the threshold gradient descent. And we obtain the similar convergence rate as for smooth optimization. So for this case, we obtain the same result if there is G or if there is no G. So this was the first problem. In the second point, we are interested in doing some least square regression. So we observe some data y, x, and y, and we want to predict the output y by some linear estimator x dot theta. So to do that, we minimize the true loss, so we minimize the quadratic function, which will be the expectation of yn minus xn times theta square. And so to do so, we can use a stochastic gradient descent applied to this problem, which will be least mean square algorithm, with a constant step size. And as output, we consider the average of the previous iterate. So it's really like as a gradient descent, but instead of the true gradient, it will be an estimate of the gradient. And the analysis from Bach and Moulin shows that if we assume that the data are bounded by R, and that the noise of the model is bounded by sigma, without any assumption of the covariant matrix. So we don't assume that the covariance matrix is strongly convex or bounded by, we don't assume any bound on the smallest eigenvalue of the covariance matrix. We can show a convergence rate of order 1 over n, which will be asymptotically of order sigma 2d over n, which is a statistical, which matches the statistical lower bound. And so our goal is to combine these two approaches. So we are interested in minimizing the sum of the square of the least square function plus any function j. But the problem is that stochastic proximal gradient descent with constant step size will not converge to the solution. So instead, we consider a different algorithm introduced by Xiao, which is a regularized real averaging. So in this algorithm, the next iterate will be the minimizer of the sum of the previous gradient, of the previous first order approximation of the function observed from time 0 to n minus 1, plus n times the regularization, plus the L2 regularization. And so we will study this algorithm under a particular setting with constant step size and with technique dating back from Polyak report. And the main drawback of our analysis will be that the convergence rate will be only in terms of the Malebis norm with regard to the covariance matrix sigma. So our main convergence result of the paper, we assume that the data are bounded by R and that the variance of the model is still bounded by sigma. And we also assume some technical assumption on the force moment on the data. And we are able to derive non-asymptotic lower bound, the Malebis distance, which we analyze. So we obtain a 1 over n square root of convergence without any strong convexity assumption on sigma. So it's a 1 over n which will not depend on the smallest eigenvalue of the covariance matrix, which is optimal for stochastic approximation, even with strongly convex assumption of sigma. So our result can be decomposed as the sum of two terms, a bias term of order 1 over n, which will depend on the distance between the true solution of the problem and the origin and the starting point, and a variance term which will depend on the noise of the statistical model. And there are also some corrective terms which come from the proof of order 1 over n squared. And for the proof technique, in fact, it is so first, it's not difficult to show that the true solution will be, like, it's not difficult to bound the variance term. And what is difficult is to obtain a bias term of order 1 over n. And to do so, you consider the difference between the iterate with noise and the iterate which come from the deterministic recursion. And you can show that this iteration, which is a difference between two iterates, satisfies the same kind of recursions. But with the only difference that it starts, since the stochastic iteration and the deterministic iteration start from the same point, there is no bias for the second recursion. So you can derive like the same bound with no bias, and then with a triangular inequality, you will be able to bound the stochastic part. But the problem is that this is only for the Malebis distance between the average theta n and theta star, and we don't have any result for the true general function, which will be the sum of f and g. But for some problem, for example, in the constraint case, where g is equal to the indicator of convex function, we have some result. So the previous result directly implies we have a convergence of order 1 over square root of n by Cauchy-Schwarz. And this convergence speed can be accelerated to 1 over n for some specific constraint problem, as shown by Ducci and Ruan recently. And we can also show some lower bound in the sense that there exists some convex constraint where the optimal rate of convergence will be 1 over square root of n. And to finish, we just show some experiments. So we did some least square regression constrained on the simplex with Euclidean geometry. And first we show in blue that stochastic gradient descent with constant step size is not converging to the solution. In red and yellow, in red and purple, we see that stochastic gradient descent and stochastic dual averaging with decreasing step size of time 1 over square root of n are slower. And to conclude that stochastic dual averaging with constant step size in yellow is converging at speed 1 over n. And also we see that the two criteria we study are behave similarly. So to conclude, we have shown that we obtain an optimal rate of convergence for composite least square regression without any strong convexity assumption, but only in terms of the Malebis norm criteria. And also we present an extension to all non-Euclidean geometry we have not presented here. Thank you.
Any questions? Yeah.
The analysis is for the, additive multiplicative noise.
Excuse me?
So the analysis for least square.
The analysis is for the least square regression, so it's a true stochastic noise.
I mean the oracle which corresponds to the gradient is the additive noise oracle in returns, or the additive multiplicative noise.
Can you repeat?
The noise is what we call usually additive/multiplicative.
Yeah, it's both.
Both?
Yes.
Both.
It's really the noise comes from. Yes. So the question was about the noise. So the noise here is really like you take the estimate of the gradient in one iteration. So it's really like it will mix a multiplicative and an additive ID noise.
Yes. One last question.
So you showed the experiment for the simplex constraint. What would happen if you do actually L1 regularization? Because I guess the theorem that the still good for the objective function.
Yes, for the objective function. So what's happened if it's not a constraint problem but L1 regularization? It was working also quite well on the objective function too.
So you conjecture that it works?
Yes. The only problem is like for now, we obtain like in function of the variance asymptotic rate of sigma 2d over n. So we never like leverage the fact of the regularization. So it's not. I mean, is not worse than without regularization, but we have nothing better. But empirically, it was working well. And
Okay.
also, like a last comment about that, since we are considering the average, we are also less performant for sparsity, because like all the iterated I will be a sparse, but the average will be less sparse than the final one.
Okay, so we have to move on to the next speaker. So let's, I think, Nicolas again.